We're going to learn about what's called effective interest rates, and these are used when we're comparing things that are not alike. So we might have, if we know we have, whether it's a loan or an investment, we have simple versus compound, and they lead to different outcomes. So if we had alternatives to choose between an investment or a loan which was based on simple interest versus another one we were considering based on compound, the method of calculation is different. Okay, so that leads to different outcomes. So we have different outcomes, which means the money owed or accumulated, if it's an investment, is different at the end. So we need a way of comparing the two so we know which one is a better choice. And even just staying within compound interest, if we were comparing loans or comparing investments, and they're all calculated with compound, there's still the matter of the number of rests or the frequency of the compounding periods. So again, we need a way of comparing apples and oranges to something that's middle ground, as it were, or common ground perhaps. In this video, we'll learn about effective interest rates, and in this video that will be given lowercase I dash as the effective interest rate symbol. Now we're going to look at it from, I guess this is first principles, so perhaps you don't need to copy this down, but I would like you to pay attention to it because it does part of the job of explaining where the eventual formula comes from. So in this case, we're looking at the scenario where the effective rate for an investment, okay, for example, is the compound interest rate that would pay the same total amount as the actual investment over the same period. So it's like an equivalent amount using compound interest. So we have $7,500 left in a will. Paula chose an investment scheme that had simple interest, 12%, 5 years. How much did she get at the end of the period, and what was the effective interest rate? So what would be the equivalent compounding rate to that? So you may or may not be familiar with P outside of 1 plus IN, but that's basically I equals P R T or P I N, and then we add the P onto it, and then we can factorize it and express it that way. That's just a version of the simple interest formula. That's not particularly important for this video, but using simple interest, whichever method you're familiar with, you would end up reaching $12,000 after the 5 years at the 12% simple. So what would be the equivalent annual compounding rate to that? Again, that's what effective rates are. You can see the I dash there. So we can just use the compound interest formula and set it up with annual rests. So A is 12,000, P is 7,500, N is 5. And we go through our familiar steps, dividing by 7,500, then taking the fifth root, then subtracting 1 from both sides, and we get 0.0986. So the equivalent or the effective interest rate using compound interest would be 9.86%, or perhaps 9.9 if you rounded it up. Don't copy that down, but that's basically a first principles way of how the formula works, which we'll introduce very soon. So compound interest rates with different rests are compared by calculating the effective rate for 1 year. An annual rest, one annual rest. So it's an annual rate for 1 year. That's what the formula is based on. So that gives us a way of comparing loans or investments. So the actual definition for effective rates is a bit more strictly defined here, or articulated here. Thus, for a given rate of interest I, compounded k times per year, we define the corresponding effective interest rate to be I dash, which if compounded annually will produce the same amount of interest per year as the other loan or the other investment. Okay, so it'll have the same effect, but it's a one year compounded annually scenario. It'll produce the same amount of interest, hence the term effective. It has the same effect. Here we have the formula which we are going to make use of in our work for effective interest rates I dash. So I dash equals 1 plus I on k, so k is the number of rests, or the compounding frequency, number of times something compounds in a year normally. I is the quoted rate, which is called the nominal rate. That's the given rate, okay? That's the figure, the percentage of the given rate. That's called the nominal rate, okay? And k is the number of rests. And so let's look at how that works. Find the effective interest rate for investments at 7.5% calculated daily. So we need to identify k and I. So I needs to be written as a decimal. Okay, so make sure you realize that, just like with how perhaps you might use the compound interest formula, its input needs to be a decimal. So I is 0.075 here because it's equivalent to 7.5%. Compounding daily means k is 365. So what would the annual compounding interest rate have to be to match a 7.5% daily compounded situation? Alright, so we can see the formula there, and then on line 3 we can see the substitutions, and when we calculate that we get 0.07788 or 7.79%, maybe if you want to round it to 2 decimal places. So something that is compounded daily at 7.5% has an effective rate of 7.79. So it's equivalent to an account that gives 7.79% compounding once a year. And that makes sense because when you're compounding more frequently than once a year, you don't need as much of an interest rate to have the same effect. Or conversely, if you have a 7.5% daily account, you need to have to get the equivalent amount of outcome, you need 7.79% compounded annually.